Good afternoon, everyone. I'm going to talk about conditional inference, trees and forests. Basically, I'm a mathematician turned statistician and also trying now to fit into the fancy world of machine learning. But what it drives me there is trying to answer questions in public health because we have very complex data, and any algorithm, any sensible methodology that will help us make or answer those questions, I'll definitely just jump onto the bandwagon. And why are we using the trees and the forests? It's not the normal forest, it's just the structure of the methodology or the algorithm. So basically, if I think of all of us here, and I want to maybe predict the spending patterns of people in this room, what the algorithm does, it goes into the information that we have about everybody in the room. Could be your gender, your place of residence, how big is your family, and so on and so forth. And then it selects one of the variables that best separates us. Okay, so if it's gender, for example, the males and females, and then there could be other embedded, within the two groups, that there are other things that would basically separate us. Then the algorithm goes on and on. For example, the next one could be your place of residence or your social status, or, and so on and so forth. So if I get a new individual, I can actually just pick that individual and then run the individual down the algorithm and then be able to predict. And with that, I can tell a story because I know he or she, a male or female, comes from this type of residence, and then I can predict that, okay, that will be a high spender, definitely. So that's what machine learning is all about. They're building machines such that when we get new data, we just feed in the data and then we get to know about you or whether we can give you a loan or something. So it goes on and on and forth, so forth. So what we're talking about here is more on the biological side of it, because I'm more fascinated with using these methodologies to help in understanding public health data and answering research questions, because we have so many complex data and complex diseases and all so on and so forth in Africa. So I've talked about the biological applications, and one of them was we wanted to know the factors affecting under 5 mortality. And the second one was what is the most efficient drug combination treatment for TB. And in the first data set, we had around 6,000 children and 19 covariates. So using the traditional methodologies was a bit tricky because there are a bit of assumptions that we have to fulfill. But the beauty with machine learning, the assumptions are not as many, so I can just run with the machine and get a good prediction. And then I can be able to make sensible conclusions. And we use 2 different algorithms. That's the tree algorithm. So one of them is greedy, because I just come here and say, okay, this is a subset of the information I know about these people. And then I split. Okay, and then I'm able to make a prediction of maybe one of the child, and then, and after one tree, I'm a device that I have several trees such that I have a stable prediction. Such that when another person comes to do the same research, they will definitely get the same prediction that I got. Okay, so that's why they advise us to do a number of trees, and then hence the forest term. Okay, and then one gentleman really said that, well, it has no statistical significance. We can't distinguish between a significant gain in information to split. Okay, so another algorithm then we jumped onto was the conditional inference forest. So this, I put in bracket, it has some form of a hypothesis test. So I say, okay, before I do the split, is this variable related to my outcome variable? So if it's spending patterns, I have to ensure that, okay, how strongly is gender related to my spending pattern? And if gender comes up top, then I'll definitely use it to split my data. And then I ask that same question over and over again until I have a tree, and then I get the forest, and then I can easily predict the spending pattern of an individual. And yes, back on our data, we ended up having some factors, sorry about the font, but we were able to answer the different predictors that predict under 5 mortality, number of children under the age of 5 in the household, and number of births in the past 5 years. And you see this is all related to contraception. But these were basically the factors that came up top. And then we were able to also determine which drugs were really instrumental in, for example, determining negative sputum conversion, that is for the TB patients. And then unfortunately, the drug combinations were not really meaningful. Like none of the drugs combination that they gave the patients were really, really effective. And we were also able to compare across the methodologies that we used. And then we came up with the conclusion that conditional inference forests are good when we have really complex data and with lots of covariates, because you have to do that hypothesis to test how strongly your variable is related with your outcome variable. And therefore, and with that, you're able to draw a meaningful conclusion, because it's very risky to come up with conclusions in public health that are really wrong. So the better the methodology, the better the results, and therefore better and meaningful conclusions. And that was our contribution. And there I used basically 2 algorithms that are almost similar, and then the CIF, as you can see. But these are basically 2, they are almost the same. One takes care of the ties, and one doesn't take care of the ties, like individuals that almost have the same survival time. But then this was the conditional inference forest, and we managed to get the lower the graph, the better the model. So the CIF had a better predictive performance, but in the less complex data, where we had only 107 patients, there were not really so much gain in the information. So thank you very much. Look forward to the questions.